Hello class, we're going to talk about several definitions now for the beginning of this class. One of the definitions is variable. So a variable is a characteristic that can have different values. A characteristic that can have different values could be anything. It could be number of hairs on your head. It could be sex. It could be how many cups of water you drink a day. It could be your race. It could be your GPA. Again, these are things that can have different values. Values are possible numbers or categories that a variable could have. So, for example, if we said GPA, a value that GPA could have would be 4.0. That means you got all A's, right? But a value couldn't be 12, right? That's beyond the capability of the variable GPA to have that value. So values are sort of the range in which a variable can have scores. So a score is a particular person's value on a variable. The book uses the idea of stress. So let's say you had a measurement of stress. You made a survey and it said, how stressed are you? And the students all took this survey. Let's say Fred scored a 12 on the stress scale. Brandy scored a 4. So those two, 12 and 4, which we looked at before with GPA, 4 could be a GPA, but 12 couldn't be. Both 4 and 12 could be stress ratings. They could be scores that people have. In fact, Fred and Brandy both have those scores. So the score is a particular person's value on a variable. A variable is something that can vary. Obviously, stress is a variable because you might be really stressed right now. You're just starting to take this class. You don't know how it's going to go, and so stress levels through the roof. It might not be as high as before our first test, but it could be pretty high. My stress is pretty low right now. I'm sitting in my house, in my garage, where I like to be, and I'm teaching something I like to do. So my stress level's pretty low, right? So it's variable. Different people have different scores, and the values of that can change. Something that is invariable would be like a constant, like pi, right? So pi is used in geometry, 3.1415962. That doesn't change, right? So circles always are going to have that same relationship. So it's invariable. That's a constant. We call those constants. Constants aren't really interesting from the perspective of people. What makes people interesting is our diversity. That makes us interesting is that we have differences on these variables. It seems like Brandy is less stressed than Fred currently, and so if we measured their scores, we see that Fred has a 12, Brandy has a 4. But that's nowhere near Janet's score. She's up at a 30. She's stressed out of her mind. And Janet's score is 30, and that's the highest score on our scale. So nobody could have like a 31, because 30 would be the highest score. And Tony, his score is a 0. It's because he's asleep, right? That's the lowest possible score you could have. He's not conscious of any sort of stress. So 0 to 30 would be our range. So the range is the lowest to the highest score that we could have. And we'll talk about range again when we do variability. But these are really important concepts: is variable, value, and score. That's all I have to say about that right now. Now that we've discussed variables, and we understand that they are just characteristics that people can have that are different from one another, we'll look at different kinds of variables. For example, there are numeric variables. Those are ones that could be, I have 3 children, so number of kids is a numeric variable. The average woman gives birth to 2.3 live births, which is weird because you can't have a 0.3 live birth. It's not like a leg and the stomach come out, right? That would be weird. So that's not what it means. What it means is that's an average. However, it's still numeric. We'll talk about discrete versus continuous variables in a second, but first we have a variable that's numeric. Now, what is that different? That's different than categorical variable. So a categorical variable is like sex, right? So I have 3 boys. I don't have any daughters. So that categorical variable of sons and daughter or sex would be male or female, right? There's no It's not like ones are female and twos are male, or twos are female and ones are male. That doesn't even make sense. But there are differences between people, and those differences, male and female, are a difference we can measure, and that's a categorical variable. Something like hair color, right? Or personality characteristic. Those are really categorical variables. They're interesting variables, but they're different from numeric ones. There's a limited set of statistics we could perform on categorical variables. We'll learn a couple in the class, but most often what we do with a categorical variable is describe how many of them there are in a particular group of people, which is what we call a sample. Numeric variables can also have further differences, right? There could be a numeric variable like, say, temperature, and we rate temperature on a Fahrenheit scale where at 32 degrees Fahrenheit fresh water freezes, and at 32 degrees Fahrenheit at sea level, at 212 degrees Fahrenheit at sea level, water boils. So that's things we know about, but 0 Fahrenheit doesn't mean 0 temperature, that there's no heat, right? We're measuring heat with these temperature scales, and 0 Fahrenheit doesn't mean there's no heat. For example, you can get to negative 15 degrees Fahrenheit. I think negative 19 is where Celsius and Fahrenheit are the same. Even Celsius, right? Celsius 0 means water freezes, and 100 means water boils, but negative 2 degrees Celsius is totally fine. So you could have that. There's no absolute 0. If there's an absolute 0, that is called a ratio scale variable. An absolute 0 means, so I have 3 children. If I had 0 children, that means I don't have any children. I can't have negative children, right? That's not possible. So the variable of number of children is a numeric variable that is a ratio scale. That means if you have 0 kids, you don't have any kids. If you have 2 kids, that's twice as many as 1. If you have 10 kids, that's twice as many as 5, right? And so it goes up in what we call equal interval variable. That's a ratio scale. And it's numeric. The number of kids you have is a numeric variable, equal interval, and has an absolute 0, so it's ratio scale. Those temperature measurements, Celsius and Fahrenheit, are not ratio scale because they don't have an absolute 0. But there is Kelvin, right? Kelvin came along and solved this whole thing. He said, hey, if we're measuring heat, 0 should mean there isn't any. So absolute 0, where there is no heat, that is a ratio scale, equal interval numeric variable. But Celsius and Fahrenheit aren't. People treat them as such. So in research, people treat them as such and use statistics on them as though they are ratio scale, equal interval. But there are other types of levels of measurement. For example, there's rank order. I have a firstborn, a secondborn, and a thirdborn. So if you did birth order, you don't know what the distance is between the time that my first son was born and my second son was born. Maybe they're twins and one was born a minute apart. In fact, they're born like 2 3/4 years apart. So that's a much bigger difference. But the amount of time that passes between when they were born doesn't matter because there's the first and then there's the second. So that would tell you that one is older than the other, but you wouldn't know by how much if you just knew it was my firstborn or my secondborn or my thirdborn, right? The difference between the time intervals of their birth, if you just know it's my first, second, or third, that is a rank order variable, not a ratio scale one. All right, so let's talk about discrete and continuous variables. A discrete variable is something where there's no intermediate values for it. So the number of times you've been to Disneyland is a discrete variable. You've been there once, twice, 3 times, 0 times. But you haven't been there 0.75892 times. You haven't been there 1.333 times. That doesn't make any sense because you either were there or you were not. It is discrete. Variables that are continuous are ones that could have continuous, if we got more and more precise with our measurements, you could continue to add decimals to the end of it. For example, I weigh 215 pounds. I weighed myself this morning. It says 215.0 on my scale. If my scale was more accurate, It might say 215.04. It probably wouldn't say 0.05 because people usually round up one, and we'll get to rounding in a bit, but that may or may not be a good policy to take when we round. But nonetheless, 215.04. And if it was even a more accurate scale, let's say I was at the doctor's office, it might be 215.043, or it might be 215.043296, right? You could continue to go further and further with your accuracy on that particular measurement because it's a continuous variable. Weight is a continuous variable. Weight is also, as you know, a numeric variable, and it's ratio scale because 0 means you have no weight, right? So if I was floating in space, if gravity didn't tug on me, I would have 0 weight, and so that would be no weight. That would be a ratio scale numeric variable like weight. So that's ratio, equal interval, numeric variables, rank order variables, discrete variables, and continuous variables. The next part of our book talks about frequency tables. And so a frequency table is the way in which we describe or we display numbers in order using a table to show sort of how often a score occurs in a sample of scores. So I need to tell you what a sample is. So if I measured all people on Earth, there'd be like 7.5 billion. That would be the population of Earth. Now, the population of Earth doesn't necessarily mean we're always studying everyone on Earth when we do something. For example, if I was studying stress, like the books use as an example, in college students, then I would only be concerned with college students. I wouldn't be concerned with, say, mid-level career professionals or elderly folks or children. I'd be concerned with college students. Now, if I wanted to understand a particular group of people, I can't measure all of them. There's just too many college students in our country for me to measure everybody, so I'll take a sample of them. And this is based on the central limit theorem and some other laws of large numbers. We can take small samples and they give us a generally good representative sample of the population that they come from. Now that's something that we'll get into more and more as we do inferential statistics. For now, just consider that a sample is a small subset of a population that we're interested in studying. So if I grabbed 10 students and I said, how stressed are you right now? I would find a score for all 10 of those students when they responded. And then what I could do is say, how often did I see, on a scale of 0 to 30, right? That was our stress scale. How often did I see students score a 4? Or how often did we see a 12? Or how often did we see a 30? And then I could mark the frequency of those occurrences within my sample set. If I displayed the frequency that we saw each of the scores in our sample, I could display those numbers in order, top to bottom or bottom to top, ascending or descending, depending on your style or what you want to show. And I could get a display of that sample visually to take the data into a more understandable presentation. So a frequency table also includes the percent of scores that were that particular score in a sample. What do I mean by that? If we had a sample of 10 people and let's say 5 of them said that they had a 12 level stress, then 12 would represent 50% of all of the sample. And so we'll take if 12 people, or if there was 10 people and 5 of them said that their stress level was 12, we would look to say, okay, there's 10 people in the sample and 5 of them, which is half, say that they have 12 stress, then we would mark next to the frequency of the score 12 in our data set, we would mark 50% because that's half of the people who were in the data set said that they had the stress level of 12. That's just one example of a frequency table. The book goes into further steps on how to create a frequency table, and a couple of things before we get started on that. The book gives you a good structure for how to do it, but it doesn't mean you have to do it that way. The reason that we display numbers in order visually is to give our audience a better concept of what's going on in the sample that we're analyzing, that we're looking at to say what's going on with the data. We want to be able to display what we've noticed about the data, so we do that. If I have 10 people in a sample and not a single person scored 30, Do I want to display the range of the data or not? It depends on what I'm trying to tell people about a particular sample. It depends on how I, as the researcher, want to present those data. But let's go through how the book talks about you should make a frequency table. First, make a list down the page of each possible value. So if you remember, our variable stress, I just made it up, has a range of 0 to 30. And if you did that, then you would start with 0 or with 30. Now, whether you want to start with 0 or 30, it's fine. Whichever you want is fine. It's going to tell you to do it from the lowest to the highest. That's what the book's going to say, but it doesn't actually matter. If you did it from highest to lowest, that could be useful as well. The only thing I want you to do is to have a reason why you're displaying those numbers, to have in your mind, what am I attempting to show my audience about the data in this sample? And you can do it any way you want. There's no law that says 0 has to be on the top and 30 has to be on the bottom. That's not true. Now, from a further standpoint, we might want to dig down into the nitty-gritty of numbers and representing things with numeric values, but that could be for a more fun sort of interactive class, maybe on Zoom later. The next thing is to go one by one through the scores, that is the data set. Those are the scores of each of the people who you sampled. And then to mark 1 for each next to its value on your list. So, right, you've listed them 0 to 30, right? And then you're going to go through your sample and say, oh, I got one person with a 4, I got one with a 12, here's another with a 12, here's one with a 10, here's one with a 12. You're going to go through and you're going to mark a little check mark, what we used to call hashtags, but you guys ruined that for us with the whole Twitter thing. And now you're going to mark, 1, 2, 3, 4, 5 for 12. Now I put the little X through it because then you can count in multiples of 5 it's helpful to do it that way. If you don't do it that way, that's also fine. You should mark the frequency, or the numeric value that represents how many of the people in your sample had that particular score. Then what you're going to do is make a table showing how many times each value on your list is used in the sample. That's the third step to do. And finally, you'll figure out a percentage. Now, how do you figure the percentage? It's easy. I used a sample of 10 people, so we could just divide by 10. Right? We said one person scored 4. So 1 divided by 10, right? That's one person had a score of 4. And there are 10 people in our sample, so that 10 people, only one of them had a score of 4. So 1 divided by 10 is 0.1. Okay, so 0.1, or 10%, if we take that decimal and we convert it into a percentage, it's 10% of our sample had a 4 in our sample. 10% of the people said their score was a 4 for stress. Next up on the docket for learning about statistics and displaying numbers in order is the histogram. The histogram is a further iteration of what we just did with a frequency table. It helps us to transition from that y as being the axis showing all the different values for the variable, all the scores of our sample, to then flipping it on its side, and now on the x-axis or the horizontal axis, we'll have the numbers or the values for each of our scores, the variable that we're measuring. Let's say stress now, 0 will be on here, and then it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 30 for our variable. And so typically what happens then is that you represent, instead of just the number of the frequency, we physically represent by a bar. This is a histogram, not a bar graph. Bar graphs typically are for categorical variables. But in this sense, on the vertical axis, the y-axis, we're going to put how often that particular score occurred in our sample. So if we had, again, no people that said they had 0 stress or 1 or 2 or 3, but we had that one person who said they had 4 stress, then we'll put a little box that represents on the y-axis 1 notch up, saying one person said they had a 1, 2, 3, 4. So we'll put a little box, and then the next one, 5, nobody said 5, nobody said 6, nobody has said 7, and we'll go up to 12, and then we'll say, 5 people in our group said that they had 12 stress. So we'll go all the way up. We'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we'll put a bar there. So that bar represents that there are 5 people in our sample that had 12 level stress. That's what a histogram does. And in histograms, we typically have the bars touching one another. So in bar charts, they're typically spread apart. What that represents is that numerically, the level of stress is going up and down continuously in an equal interval range from 0 to 30, that it's a same distance apart from each of these. Now, if you think about it, how much is someone's stress? Is a 5 to a 6 the same as from a 7 to an 8? Might not be the same way, right? That might not be the same level of stress. And so this is more like a rank order variable, but we treat them as though they're numeric and ratio scales. Even though they sort of, the construct validity of whether or not we're measuring stress on this sort of self-report measure might be wrong. You might be questioning that right now. I get it. You guys are really smart. We're going to treat it as such, just to learn this stuff. All right, the last part of chapter 1 really talks about math anxiety, and that's something that many of you probably have dealt with before, where you're not really confident in your ability to do this math, but you want to. You want to get through this. You have a goal. You have an objective that you're attempting to meet, and the curriculum suggests that you have to take this math class, but yet you still find yourself experiencing math anxiety. So what is math anxiety? Well, it's something that students who particularly don't like math or haven't really been taught to like math, they experience when they encounter problems that they don't know what to do with. Now, I want to make sure that you realize there's no real consequence. There's no foot that's going to drop on you if you don't understand how to do something. Sometimes that feeling where you feel stressed about not knowing how to do something can make you want to stop. And that's really where math anxiety gets in the way of students progressing. I don't want you to stop. I want you to contact me. I want you to contact a friend who's in the class. I want you to contact a former professor that encouraged you. I don't want you to stop. Try. I'm like the opposite of Yoda. Yoda's like do or do not. No, I'm like try. Because eventually trying can lead to doing, especially if you take those errors or the lack of competence that you currently have and you move towards a place that you gain competence. So math anxiety is something that's normal to feel. If you feel that, great. It's not something that should be uncommon in this class. A lot of people report experiencing math anxiety. If you're experiencing that, that's fine. I'm not worried about it. Talk about it. Tell me, I have math anxiety. What I can help you do is help you develop some resilience, some competence where you gain confidence with each of these successes. Like I told you about, some of my struggles was that I didn't recognize as I was gaining competence. I didn't have anybody telling me, oh, you were gaining that. So I didn't really understand how much the time and work and effort I was putting in was getting me systematically better. So I can be able to help focus you and encourage you that you are improving with the time and the effort you're putting in. But I need from you to not deny that you're feeling anxious, and also you need to trust me that we can get you to the place you need to get mathematically. You're capable of this. I not only believe in you, I know that you can get through this. I know you can because I've watched students just like you do this all the time. They come in with the same math anxiety every semester. That's why there's an even little box in the book that talks about it at the end of the first chapter. This is not uncommon. Your experience is something that people can deal with and in fact thrive after they realize it's okay to try, it's okay to fail, but it's really important that when we try and fail that we recognize what it was that made us fail, and then we attempt to change that variable a little bit. We attempt to move it into a place where we get better from our failures. We own our failures, and we say, well, what do I need to do now so that that failure doesn't continue in the future? That's something that I want you guys to have some experience with this semester. I'm going to make you fail, and I want you to take those failures and then improve yourself based on them. If you have a math anxiety, contact me, let me know. Don't worry about it. It's not something that you should be ashamed of, and it's something we can deal with and will in fact make you better, not just in math, but in all areas where you have some lack of confidence.